Everyone, today we're going to talk to you about something super cool called gravitational waves that astronomers right here at RIT study. Gravitational waves are ripples in the very fabric of space and time itself, and we can detect them right here on Earth. So we're going to learn a little bit more about what gravitational waves are, how they're formed, and how we detect them.
Imagine, during a sunny day, to look at the reflection of your face in a lake. The reflection is almost perfect, but as soon as someone throws a rock in the water, the reflection will be distorted. This is something similar to what happens when a gravitational wave traveling through space reaches a body. The body will be stretched and compressed, as it happens to the image in the water. But what is the rock that creates gravitational waves?
When huge stars run out of energy and die, they collapse into a black hole. And since many stars live in pairs, these black holes can come in pairs that orbit each other. This orbit creates the type of these ripples that an Earth-based detector would be able to see, while a space-based detector could see ripples from sources like a black hole eating a star. But how exactly do we detect these ripples?
When these kinds of sources send out gravitational waves, the ripples travel really far. They move through space at the speed of light, and once they reach Earth, scientists use LIGO to detect them. LIGO is an observatory made of lasers and mirrors, and there are 2 sites in the US, one in Washington and one in Louisiana. Each site has 2 perpendicular arms that are 4 kilometers long. Imagine the Golden Gate Bridge lined up 4 times! That's huge! Inside each arm, there's a laser beam traveling the whole length of the detector. When the laser is turned on, it's split in half before traveling down the length of an arm to a mirror, where it's reflected back the same direction it came. It meets back at the middle with its other half, and if there aren't any waves, the 2 beams cancel each other out, and there's not anything to see. However, gravitational waves stretch and compress the long arms, changing the paths of the laser so that they no longer cancel out. Scientists track these disruptions, which are a fraction of the size of a proton. This means the detector is extremely sensitive.
LIGO isn't the only gravitational wave detector. LISA works a lot like LIGO, but it's going to be in space. And then Nanograv uses a type of dead star called a pulsar in order to detect gravitational waves, and they're really close to their first detection. Whether you're interested in finding little black holes using LIGO, medium-sized black holes using LISA, or supermassive black holes using Nanograv, people here at RIT do all 3.